In this video, we solve problem number 4, or actually I think it's problem number 3, from quiz number 5 in the spring 2021 semester from version 3 of this quiz. This problem covers standard G20, which is about variation of parameters. So the problem statement says, the following set of functions includes two known linearly independent solutions of the associated homogeneous differential equation on the interval from 0 to infinity. So we know that y1 equals x plus 2 causes this left-hand side, if we evaluate it, to be 0, and y2, which equals e to the x over 2, causes this function, or this linear combination of functions, to be 0. Those are solutions to the associated homogeneous DE. It says use the fundamental set of solutions above to find the general solution of the differential equation below. It's a non-homogeneous equation using variation of parameters. So first of all, they're telling us that y1 and y2 are two linearly independent solutions of this problem where the right-hand side is 0. So that means that y sub c is c1 y1, where y1 is x plus 2, plus c2 y2, or y2 is e to the x over 2. And now we want to solve the non-homogeneous problem using variation of parameters. So we're going to let y sub p equal u1 y1 plus u2 y2, where u1 and u2 are not constant functions. Now remember, when we derived this method, we took this, we differentiated it twice, we substituted it into the differential equation. We ended up with one equation with way too many unknowns. We simplified it, we rewrote it. Eventually we got down to one equation with two unknowns, u1 prime and u2 prime. And then we made a choice that turned that one equation and with two unknowns into two equations with two unknowns that we were able to solve using Cramer's rule. So that's what we did to come up with these formulas. Now, I told you that you're going to be able to skip some steps. We're going to skip the steps this time. So we're letting y sub p equal this. If we do that, I'll say then, by variation of parameters, which I'll just abbreviate v of p, u1 prime turned out to be w1 over w, and u2 prime was w2 over w, where the w's are related to the Wronskian. So the first w is the Wronskian of y1 and y2. And w1 looks just like the Wronskian, but you replace the first column with 0 and f of x, where f of x is not the right-hand side, but it's related to the right-hand side. It's the right-hand side that you get after your leading coefficient is 1, set equal to 1. So we're going to divide everything by 2x here. And if we simplify that, we end up with a negative 1/2 x. As one of those x's will reduce, we end up with a single x in the numerator. That is our f of x. So that's our w. w1 looks like that, where f of x is this, and w2 is very similar. You just, instead of replacing the first column with 0 and f of x, you replace the second column with 0 and f of x. So I want the formulas for u1 prime and u2 prime here, and then the formulas for w, the w's. Okay, in order to find this, we need to find u1 prime and u2 prime, which means first we need to find the w's. We'll substitute them in, then we'll know what the derivatives of u1 and u2 are, and we'll take the antiderivatives to get u1 and u2 back. Once we have those, we'll plug them in here. That'll be our y sub p. Y sub c plus y sub p will be the general solution. Okay, so that's the plan. Let's find our w's. W is the Wronskian of y1 and y2. And y1 was just the function x plus 2. And y2 was the function e to the x over 2. So take the derivative of that, you get 1. Derivative of e to the x over 2 is e to the x over 2 times the derivative of the inside. You could think of that as a 1/2 x. The derivative of a 1/2 x is just the constant, the 1/2. So we're computing w now. And when we evaluate this 2 by 2 determinant, we multiply across that diagonal and multiply across that diagonal and subtract. Now this I'm thinking of as a binomial because it is, and I want to take this guy and I want to distribute it to each term separately. So I have 1/2 times this times the x. And I'll write it in the more traditional order. And then this times 2 is going to give me the 2 times 1/2, which is just 1 of those. And then we multiply over here and we subtract. So those guys are gone. And our w just turns out to be 1/2 x times e to the x over 2. Okay, now w1, whoops, having a lot of problems with my camera today for some reason. w1 looks just like that, but you replace the first column with 0 and f of x. And we said that our f of x was negative 1/2 x. So I have negative 1/2 x here, e to the x over 2 here. So we'll do this times this, which is 0, minus this times this. We have 0 minus a negative, so that's adding 1/2 x e to the x over 2. So we just have 1/2 x e to the x over 2. And w2 looks just like the first one, that Wronskian, but you replace the second column with 0 and f of x this time. So we've got an x plus 2 and a 1, and here we have a 0, and f of x was negative 1/2 x. So if I multiply those guys together, distribute that negative 1/2, I have negative 1/2 x times x is going to give me negative 1/2 x squared. And then negative 1/2 times, or negative 1/2 x times 2 is going to give me a negative 1, multiplying the coefficients times an x. And then we're subtracting 0, which of course doesn't do anything. Okay, so we've got our w1 and our w2, and that's enough to substitute into our formulas to find u1 prime and compute the antiderivative of that. So u1 prime is this, and w1 was 1/2 x e to the x over 2. Now w also happens to be 1/2 x e to the x over 2, so that's convenient. As long as x is non-zero, we're going to get 1. So that's great. u1 is then the antiderivative of 1 with respect to x, so that's x plus a constant. And we don't want a constant times y1 as part of our y sub p, so we choose that constant to be 0. So u1 is just x. All right. And we'll do something similar to get u2 prime. u2 prime is w2 over w. So this is negative 1/2 x squared minus x divided by 1/2 x e to the x over 2. That one looks more complicated. But we can still deal with it. We can still handle it. What I would recommend is factoring out a 1/2 x from up here. So I say 1/2 x times what will give me this negative 1/2 x squared. Well, I left the negative inside. Well, maybe I shouldn't have. Let's factor out the negative as well. Factor out the negative 1/2 x. Well, negative 1/2 x times 1 more x would give you negative 1/2 x squared. Then ask yourself, negative 1/2 x times what would give us a negative x? Well, negative times a positive would give us a negative. And then I would need a 2 there in order for the 1/2 and the 2 to give me a negative 1 in front of the x. You can distribute and see that that's the right thing. Okay, so now I have this. The 1/2 x and the 1/2 x reduce. Now I've got x plus 2 times negative 1 over this exponential. Or if you want, you can bring that exponential up to the numerator. Probably a good idea, so you can take the antiderivative. Alrighty. So that means u2 is the antiderivative of negative 1 times x plus 2 times negative x over e to the negative x over 2. So I've got a polynomial times an exponential. I would use integration by parts, and I would let u be the polynomial and dv be everything else. Since u is a polynomial, tabular integration by parts is probably the way to go. So I've got negative 1 times x plus 2 here. The derivative of x plus 2 is just 1. So I'll have 1 times a negative 1, which is negative 1, and take the derivative again, and you get 0. Over here, we've got a negative x over 2, or e to the negative x over 2. The antiderivative of that is this, divided by k, where k is the constant inside, multiplying that x. That's a negative 1/2 x. So I'm dividing by negative 1/2, which is the same as multiplying by a negative 2. And if I do that again, I'll multiply by another negative 2, and we'll end up right there. And then when we do tabular integration by parts, we multiply across this diagonal, multiply by positive 1, and then we add what we get when we multiply across this diagonal, multiply the result by negative 1, and then we add, and we've run out of rows here, so then we add c. So we're going to get this times this, negative times negative is going to give me a positive. Minus this times this. So minus a negative is going to be a positive as well. Plus C2, you're going to choose C2 to be 0 because we don't want a constant times y2 as part of our y sub p. And if you want, you can distribute. This is 2 times x, 2 times 2 is 4, times that exponential plus that other 4. And the constant of integration we've already chosen to be 0. So u2 is actually 2x plus 8 times this exponential. Okay, great. So we found u2 prime, and we computed the antiderivative of that. And now that we have u2 and u1, we can substitute to construct y sub p. So we'll substitute u1 and u2, and of course y1 and y2, and then simplify to find y sub p. Now u1 was just x. Now y1 was x plus 2. Don't forget your parentheses because you're going to have to distribute that x. Then we're going to add u2, which is 2x plus 8 times this exponential, times y2, which was this exponential. Well, e to this power times e to that power, just the sum of the powers, e to that, the sum of the powers, but this plus this is 0, so we're going to get e to the 0 there. So that's 1. So we end up with x squared plus 2x plus 2x plus 8, which is x squared plus 4x plus 8 as our y sub p. And then the general solution is y equals y sub c plus y sub p. In this case, it's going to be c1 times x plus 2 plus c2 times e to the x over 2 plus this second degree polynomial. And I think we did have a restriction on x. X can't be 0. Even though it looks like x can be 0 here. I don't know. If x is 0 here, we might have a problem as well. So, well, it says on interval from 0 to infinity. So we'll state that as our interval of existence. And I think it makes sense because x equals 0. When x equals 0, that second derivative term disappears. So it's like, it looks like a first order equation. Something weird happens at 0, so we don't want to plug in 0. So that is our general solution.